So at this point, we're going to talk about multisets. A multiset is a variant of set. It's also, of course, implemented under the hood with a balanced binary tree using a red-black tree. But the single biggest difference between a set and a multiset is that a multiset can contain duplicate keys, whereas a set can't. And if you think about how this works with the tree, what it does is when it goes to add an element into the tree, it finds the element. And for a normal set, there can only be one element with that value. With a multi-set, you could imagine having basically a linked list of elements that all have the same value. And so they'll all be stored multiple times. So what would be an example of something that might be a multi-set? It might be a set of student names, for example, or it might be something you could use for various kinds of set operations like set intersection or set union or set difference and so on and so forth. So there's lots of very legitimate use cases for multi-sets. So now we're going to talk about multi-sets and show an example. So you can see here, as I mentioned before, a multi-set is just a regular set, except it supports multiple keys. It has the same signature. It takes a type name, which is the key type. It takes the comparison functor, which defaults to less, and it takes an allocator, which defaults to using the global operator new and delete. It's got very much the same characteristics as a set. You can store objects of the keys in a sorted manner because it uses a red-black tree under the hood. Its value type as well as its key type is the key, and you can have multiple items with the same value, so it supports duplicates. And multi-sets are particularly well suited for set-related algorithms, things like set union, set intersection, set difference, set symmetric difference, and so on and so forth. And the reason why sets are good is, of course, these set algorithms all expect the items that they're working on are sorted. So that works really well with a set. And the output of these algorithms is also always sorted, and that works well. And you can see that another nice property of multi-sets, and sets for that matter, is that inserting new elements into a set or a multi-set doesn't invalidate iterators to existing elements. You only will invalidate iterators if you erase an element that you have an iterator to. And then, of course, all bets are off because you've gotten rid of the underlying node in the tree, so obviously it wouldn't be valid anymore. So let's take a look at multi-sets using several STL algorithms. And we're going to use these with some of the algorithms that are part of the set algorithm category. And we're going to come back and revisit set algorithms later. So I won't spend a lot of time on the algorithms themselves. I'll just kind of show you how they work, and I think you'll have a pretty good intuition just looking at the example here. So we're going to start out by creating two sets, A and B, which I give a bunch of numbers to, which will be sorted, of course. They're sets of ints. Then we create an empty multi-set C, which we'll use to store the output in for some of the set algorithms. We copy the contents of set A, we copy the contents of set B to print their values, and then we go ahead and we compute the union of set A and set B, and we write that to the standard output. And of course, set union, you probably know, hopefully you've taken enough math to know what a union is. It basically says the union of two sets are the elements that are in set A, set B, or in both set A and B. So it's combining all the things that are there. And so we print the results. Then we're going to do set intersection. Set intersection basically says only create me an output set that will be consisting of the elements that are in both set A and set B. So once again, we give it set A and its range, and we give it set B and its range. And in this case, it's going to print the output to the output iterator, which we're going to use as an output adapter for an O stream for the C out, just like we did for set union. Then the third example here, which again, we'll talk about these algorithms in more detail later, but the third one is the set difference. And this will find the elements in set A that are not in set B. So it's the difference between the sets. And in this case, rather than writing this directly to standard output using an O stream adapter, instead we're going to use an inserter, and we're going to add each of the elements in this set difference at the end of set C. Now, if you recall, if you go back up to the top, set C originally started out being empty. It had no elements in it whatsoever. And so what we're doing here is we're going ahead and using this thing called an inserter. And an inserter is essentially an iterator adapter that converts some container, in this case a set, to be used in the context of an output iterator. So we're making it possible for this inserter function to wrap our set up in a way where the assignment operation will add an element at the end of the set. Now we're going to talk a lot more about inserter adapters and iterator adapters and all this kind of good stuff, probably either later this week or early next week. I think we'll probably get to it this week. But for right now, just take it on faith that that sticks it at the end of the set. And when we're done, we then go ahead and use copy to copy from the beginning of the set to the end of the set. And I can use, I should probably get in the habit of using cbegin and cn just to make it clear these are consts. And they go ahead and copy the contents to the standard output. So let's go ahead and run the code. And you can see here that we end up with this output. So the first set contains those elements, the second set contains the other elements, and then the union of those sets, of course, include the elements that are in both sets. The intersection includes the elements that are, the union includes the elements that are in either of the sets. Set intersection includes the ones that are in both the sets, and then set difference includes the elements that are in set A that are not in set B. And so you can see there's different output for each of these different variants. And the version that used the set difference stored it into the set C using an inserter adapter to adapt the set container into something that would work as an output iterator for the copy algorithm. And hopefully at this point you're familiar enough with what copy does to know what the input iterators do versus the output iterators. Input iterators give you the range to be read, and then the output iterator gives you the thing to write to in order to do some computation. In this case, add something at the end of the set.